Hi guys, wanted just to do some refresher on some concepts that we've covered thus far. First thing is the two types of force that we've covered so far. So we've talked about two main categories, which are non-contact forces and contact forces. Non-contact forces have an indirect effect on each other, and that's usually done through fields that are being created, whereas contact force require the physical application of a force that can be seen. Um, we've talked about some particular forces that have been important to us, and we've been talking about weight, Fg. Fg, we've done an investigation where we saw that the relationship of Fg, or weight, is equal to the mass of an object and the gravitational field experienced by an object in a particular system. It could be a planet, an asteroid, or a star, and that's denoted by the value of G. For us, it's 9.8. We've talked about the normal force, and the normal force denotes any opposing force to a weight force. So I guess you can interpret it as the pressing force. So an object resting on a table will experience a gravitational field drawing it towards the center of the Earth, but yet the table would actually stop that from happening due to the atomic bonds of the table, and that's creating the pressing force there. The other one that's been very important for us to analyze is friction. Now, friction force here has been capital F, small a subscript f, is denoted by this special relationship with this coefficient. It's called the coefficient of friction. It's denoted by this Greek letter mu, which looks like an odd U. And what that is just an empirical value that relates to different surface and how difficult it is for them to slide past each other. That's what that number is, and it's usually some small number, and it deals with the ratio of the forces acting between two objects, but they're usually given to us. The other one is you can see then the normal force appears there again, and this one is denoted by the variable capital F subscript n, and that appears there when it comes to objects experiencing frictions. Okay. I want to go over quickly Newton's laws. Now, we've spent some time talking about Newton's laws, but I feel like we haven't given them their day in court. So let's have a look at this one. So Newton's first law all has to do with objects either being static, that they're not moving, or they're in some kind of equilibrium between forces, right? So if they're in equilibrium and they're in motion, they're going to be expected to be moving at a constant velocity because of that, because the forces are cancelling out, and therefore there's no net force acting on the object. In real systems, like in real life, there's always a net force which will eventually slow that object down. So we're talking about idealized systems there, but it still gives us foresight into solving different problems. It's saying that if all the forces are being added up on a system, and they're equal to 0, well, they're meeting that condition that the object is either in a static state of equilibrium, or it's moving in uniform motion. Okay. A concept that we haven't really spoken about is inertia. So inertia is an object's sluggishness or reluctantness to want to move. So Newton's first law kind of covers that as well. It's saying that, yes, the object is in equilibrium, and it's another force to get it to start moving because it's static. That's its preferred state. And in order to get that object to start moving, it requires some kind of effort to initially start to move. And that initial reluctance for the object to start to move is called inertia. Now, Newton's second law gives us a definition of what a force is and it's saying that all forces relate to the object that's experiencing the force and the acceleration that it's experiencing. So if we have those two variables, we can define the force experienced by an object. That was what that's what being said there. Now, Newton's third law is kind of the most intuitive thing that you can hear, and it's got a poetic sense to it. So it's this idea that for every force that you apply, there should be something equal and opposite to that force that's being applied. And there's always an interrelationship between forces. This one gives us a little bit of foresight. If we think about, if you look at the image here of a block being pressed against a table, what Newton's third law tells us is that sometimes these forces that fall in the same axis, here we've got the y-axis, they can add up and they can equal each other, right? So that gives us that foresight about some of the forces having a relationship, which we can extrapolate their value from, and that comes in quite handy. Okay, I've created this list for you guys, and this is to help you, I guess, tackle your different dynamic problems. So dynamic problems have to do with forces acting on objects and calculating net forces and calculating acceleration experienced by objects. So this includes both objects on a flat plane, on a parallel plane, and objects on an incline. So you can use these same rules to solve those problems. So again, every time you start reading problems or looking at the diagrams, see what variables are given to you, and just list them on the side of some kind of column that you create. Now, if the axes haven't been provided for you, make sure you draw those axes, right? Denote your vertical, your y, and your horizontal, your x, and choose your conventions. Which one's going to be positive? Is to up going to be positive? Is right going to be positive? Choose where your convention is going to be. Once you've done that, go through the three laws, Newton's three laws, and see if you can get a feel for the problem. So we'll start off with Newton's first law. Do they have multiple forces? Do you have to do some of these forces cancel out? Do the vertical forces cancel out? Does the weight and the normal force cancel out? Or maybe horizontal forces? Maybe it's an object dangling from a couple of strings, and there's no real horizontal forces acting on the object. So therefore, they might cancel out. So start thinking about that and start making predictions as soon as you can when you see those problems using Newton's first law. Moving on to Newton's second law, start thinking about the net force of the object and where is it going. Is it on a surface? Is it expected to move horizontally? Is it falling? Is it free falling? Maybe it's expected to move down vertically, or maybe it's a bird's eye view of the object, and it's got different forces acting in different directions, and you have to kind of mitigate where it's actually going to move, right? By calculating that force and kind of predicting where it's going to go. And lastly, use Newton's third law and see if any of the forces equal each other or are equivalent to each other, because that can provide some help when you might have a variable that you don't have to solve an equation with. You might have to kind of see what forces are equal to each other and therefore use those forces instead of other ones that are unavailable to you in order to solve that particular problem. This one particularly deals with the balancing of the weight force with the normal force. That's kind of what that third law looks at. As you can look at my diagram there, I've got the blue vector, which is my normal force, and my weight force, which is the red vector there. They're both the same magnitude, and they're synonymous to each other. So if I need the normal force for the value to use in my equation for friction, I can just use the weight force instead of the normal force, and that's kind of a way to go around it, because Newton's third law says that they're both equal and opposite to each other. Anyways, once you've analyzed the problems using Newton's three laws, start resolving any vectors that you have that are diagonal, right? Break them down into x and y components. And once you do that, calculate net force on the object, and then you can solve for any acceleration and any other things that you're expected to do for that particular problem. Okay.